Good afternoon, everyone. Welcome to the lecture on atomic layer deposition for catalyst preparation. This is the 11th lecture of the course and the third last lecture. And I think that this is a nice place to have this lecture. This is a specialized technique for making catalysts, not mainstream, but very interesting scientifically and for my own research as well. So the lecture contents today will be a general introduction to atomic layer deposition. What is it? Some words on the history of ALD. That has been kind of a work hobby of mine in the last years, if not decades. And we'll go through also how you can control the metal loading by ALD. And we'll go through one case example of literature where ALD overcoatings have been used to prevent deactivation. That's a paper that made to the Science journal, if I remember right. That's one of the more prestigious ones, not my own work, from the literature. And yeah, conclusion and quite many bonus slides. So this is the topic of the course that I am the best specialist in. We also will use Presemo again today, again with a code that you will need to look through here. If we look at the learning outcomes of the course, well, this is about catalyst preparation, obviously, but then, like I think in almost all lectures, we are touching a little bit the other points as well. And if we look at the learning outcomes for today, well, you should be able to describe the principles of ALD if that's going to be asked in the exam. And also you should realize that the views on the history of ALD, they are at the moment developing. This is not something where everybody in the field would agree, but this is something that is progressing at the moment. And yeah, I think it would be good for you to learn, if not the 5 ways how to control the metal loading by ALD, at least 3 or so, and know some benefits and limitations of ALD. And so you have already probably seen, I have here a flashy thing. So this is an example of an application of ALD. Here is an ALD film that is making the light. It's a transparent electroluminescent display. I got this from the Benek company who are producing these types of displays. And then I have here some films that have been made on silicon wafers by ALD, double-sided coating, and they look a little bit boring because it's the same color everywhere. It means that they are very uniform. That's the benefit of ALD. And then I have here a conformality test structure that you can have a look at. And if we talk about dispersion, here's my example again of that. I'm gonna switch this off for now because otherwise it makes noise for the lecture capture. Let's go to Presemo to get started. And there will be a warm-up question for you. Again, just to see that everybody gets there. This one is about the values of Aalto University. Your favorite value. Up there at the moment. I think I should see more. Okay, and let's see if I can get this for you visible also. Oh, no, it's not there. This is always the... Here. Ah, there's nothing to see yet. Okay, let's show the results. Yes, our favorite value. Okay, integrity is a really, really important value. Passion for exploration. I'm going to also click the courage to influence and excel. That is one that speaks to me because you really have to have some courage to influence. Okay, but the real things. I'll take this away. Which of these have you heard of? And I will show it right away. There are terms. Please read through and click each one that you have heard of. ALD, everyone. Atomic layer epitaxy, that's an old Finnish name for ALD. That is how it was invented in Finland. Molecular layering, old Russian name for ALD. That's how it was invented in Russia. Molecular layer epitaxy, old Japanese name for ALD. That's what they started calling it when they started in 80s to work with it. Molecular layer deposition, that's the organic variant. And Suntola, the Finnish inventor, and Valentin Alaskovsky and Stanislav Aalto, the Russian inventors. I still have here another question. Which of these technologies or applications you are aware of? Which rings a bell? And you can of course click in. I think that the system has stabilize. So these all are applications of ALD. In all these applications, either ALD is used or has been investigated. So electroluminescent displays, the one that was flashing over here, this is the first industrial or commercial bigger application of ALD produced in Espoo since '85. And DRAM chips, logic chips, they nowadays use ALD. So this computer has ALD in it, and your mobile phones. And many others. Today we will just talk about heterogeneous catalysis. It is a little bit different application than ALD. We are talking of different types of materials than people usually talk. We are not talking of thin films. We are talking of powders, and that sets really different types of requirements for the reactors. Still, the chemical principles are the same, but the reactor details are quite different. I think this was the last warm-up question. Yes, so then let's see if I'm able to get us back to this same mode where we were. And still this or this. Oh, no. Okay. This. Yeah. Good. I lost one scene from me, but we'll live with this. So, introduction to ALD. ALD is a chemical vapor deposition technique. We are using chemical reactions that come from the gas phase to the surface. This is and here is a proposed definition for ALD. It's from my own review from a long time ago. This is the second most cited review of all times of ALD at the moment. And so I tried to create a definition because nobody had created a definition before that. So that means that there are important words condensed to a short sentence. But in practice, so ALD is based on, some people call it self-limiting reactions. I have called it self-terminating reactions, gas-solid reactions. We have some solid where we are going to grow material. We have gas phase compounds, typically at least 2. There can be more. And these have to be compatible in the way that when they are reacted one after each other, they always contribute to a growing material layer. So this is an example where you would have typically a metal reactant, so a metal atom in the center and ligands that help to transport the metal to the surface. The metal reactant reacts with some reactive sites on the surface, and often some gaseous species are released. This could be trimethyl aluminium. This no longer works. Okay. That could be trimethyl aluminium, and the byproduct could be methane. Then the excess reactants are removed so that we have a clean system, typically in some inert gas, but it can also be in vacuum. And then you bring in the other, or the second reactant, and that reacts with the surface left behind by the first reactant, in a way regenerating it so that we can continue the cycle. In this cycle, in each reaction, you are growing some material to that. So if you would be monitoring the mass, like some people do, I never had that in my reactor, and you would, let's put here time. Typically you would have, in the first reaction, the mass would increase and then stabilize to some level. Then when you bring in the second reactant, the mass can increase or it can decrease. Actually, quite often decreases if you have heavy ligands that are being removed. And then again, this is something that you repeat as many times as you want to grow the film. So, self-terminating, what does that mean? Well, at least I interpret that means in just standard chemical terms, saturating and irreversible. So saturating means that, well, once the surface has reacted with as many reactants as it can, then no longer the reaction takes place. And then also when you stop the reaction, when you evacuate or remove the extra reactants, then you still keep that amount on the surface. So that's what is irreversible. So you cannot have, you do not do ALD growth through reactions that would not saturate. That's the first example there. So there the amount adsorbed would not settle to any value. It's not adsorption controlled, but it would be controlled by time. This is the typical CVD, chemical vapor deposition case. So even though ALD, it's one variant of chemical vapor deposition, it is its specific type. So the typical CVD would be continuous with time. ALD is not. Then unsaturation, we also need to make sure that we give the system enough time or dose to get to that adsorption controlled level. And also if we would have reversible reactions so that the compounds would desorb, that again would ruin our surface control. So there are actually quite strict demands for how the reactions should be so that it behaves in the ALD way and we get the benefits that we want. So yeah, ALD, it's basically just chemisorption, and we have been talking about chemisorption in this course. We had a dedicated lecture to adsorption. So everything that has been said about chemisorption is valid for these individual ALD reactions. the last one here is in green, so monolayer adsorption. That's very important. That is the one that terminates the reaction. We are not going above a monolayer by definition. But how do we define a monolayer? That's another question, and that's a question that is confusing people because there are many possible ways. But let's not jump to that yet. So a typical characteristic of ALD is that the film thickness, like in these cases, is controlled by the number of reaction cycles. I think I haven't written here how many cycles these have been, but I would guess that it's something like 1,000 cycles. So then the film thickness is just directly proportional to the number of cycles. And here is a reconstruction of the very first experiment in '74. That's a silhouette photograph of Suntola taken a few years ago by myself. And then it's a reconstruction of the reactor. So Suntola came up with the idea to just evaporate metallic zinc and elemental sulfur and bring these to a surface one at a time. Or actually, he had a rotating reactor where he brought the surface to these reactants one at a time. It rotated, I think, 2 times per second. And he was observing the color of the film that grows, really like the reconstruction says. And from that, he was expecting to get a monolayer per cycle. That has been that. Here we come to the definition of the monolayer also. And so he was expecting to see these purple colors, which he knew would correspond to a certain thickness of zinc sulfide. And they came, but they came later than what he was expecting. So it was actually a really, really successful experiment, right away the first one, but it was a disappointment for him because he thought it's going to be a monolayer. It was just 1/3 of a monolayer. And it was reproducible. There are these 2 experiments like plotted there. It took a long time to understand why you get this 1/3 of a monolayer, why not a monolayer, and this is something that is still causing discussion for different processes. Why do we get exactly this value that we do? So when we look at the big picture, the film grows linearly with cycles. But when we look at the very beginning, this is not necessarily true. So if we think that on a catalyst support, for example, it could be aluminum oxide, and we could deposit nickel oxide or gold or whatever there. And so the first time these molecules come, they see the oxide, they chemisorb in a certain way, then the ligands are removed by some way, and then in the second cycle, the reactant that comes from the gas phase, it doesn't see anymore the same surface as in the first reaction cycle. So that's why also the amount that chemisorbs can be different. And there are examples where the first cycle gives more material than the coming cycles, or where the first cycle gives less material. These are all have all been observed for different purposes. But this is an effect that typically vanishes after a few cycles, or if you have severe island growth, it might take 100 cycles. But anyway, it typically vanishes.
Can I have a question?
Yes.
Then the left curve is correlated to the curve A. It should be linear.
You know, we actually don't know. We actually don't know because these are already for hundreds of cycles. So you really need to investigate those very first cycles to be able to see this. So if you only grow films in 100, 200, 300 cycles, you are obscuring the very first cycle. So you don't know. So this must have been a glass substrate. I would not know, actually. There might very well be that there's an initial regime where the growth is a little bit different.
And the x-axis of the left curve is kind of correlated to the number of cycles.
Yes, yes. It could be indeed. So here it is time, but there is a certain cycling time, of course. And I think that this was something like 2 cycles per second. It's a so-called spatial ALD reactor where it's not the gases that come to the surface that are switched like nowadays typically, but the gases are stationary and the substrate is rotating. And this is something that has become popular again. There were tens of years that people didn't do this at all. Yes, it's the International Year of the Periodic Table, and it was the periodic table that inspired Suntola also to come up with ALD. As he has told, and as has been written down in an essay. So he wanted to make electroluminescent displays, and he was thinking how to get there, and the idea came to him that if you use compatible elements, that these would be more strongly bonded to each other, to the other element than to itself, so that you would be able to make a stable monolayer, as he was thinking, on the surface, which is stable enough so that you can dose the next one. And that's how it all started. Nowadays people use other types of reactants, not so much elements, but this still works. Here is a short summary of different types of metal precursors or reactants that can be used. Actually many different types of compounds. So elements, that was the first one used in Finland. Halides were the first ones used in Russia. In St. Petersburg, they came up with the same technique. Organometallic compounds, where you have a direct bond between carbon and the metal. Trimethyl aluminium is the prototypical one. Also, cyclopentadienyl compounds, these are the kinds that are used as polymerization catalysts, but they can also be used as sources in ALD. And then different types of compounds with oxygen or nitrogen or sulfur bonding to the metal. You can have a look at the reviews if you like, and then in the extra material there are still links to reviews. There have been, I think, more than 200 reviews written of ALD at the moment. And also, you, as the non-metal precursor or reactant, you can also use many types of compounds, but these simple inorganic compounds like water, ammonia, hydrogen sulfide, those are the most typical ones. Again, you can look through other references for more details. Then there are also so-called energy-enhanced variants of ALD. For example, that some metal reactants, metal compounds, they don't react with water, so that would not give, those would not be compatible to make an ALD process, but they may react with ozone, so ozone is more reactive. And then there are plasma-enhanced processes where these molecular gases like oxygen, nitrogen, hydrogen, they are transformed into plasma in the gas phase, and these again are able to remove the ligands of some metals. But I will not talk about these energy-enhanced ALD processes here anymore, because if we talk of high surface area powders, then at least I am very skeptical whether you could ever get a uniform coating inside these. You have long diffusion paths, and even ozone will not be stable enough to go inside, and plasma still much less. But these are being industrially relevant at the moment. And some examples of ALD processes. So again, the first one, just simply zinc, sulfur in gas phase, giving zinc, sulfur, and no byproducts whatsoever. The first one. Then the trimethyl aluminium water process to give aluminium oxide and methane. This I'm calling here the prototypical ALD process. I wrote a review of that surface chemistry myself when I was a postdoc at IMEC in Belgium. And partly because of that and partly because it's just ubiquitously used and studied, it has really become the most used and most studied and perhaps best understood ALD process, but still there are questions in the surface chemistry of that even that people do not fully agree. Then another type, titanium tetrachloride, ammonia, gives titanium nitride. This is also industrially used. This is a different type and an interesting type because here, okay, hydrogen chloride obviously comes as a side product, but then I'm not sure if people fully know even what are others, because here the metal center gets reduced. We have a titanium in oxidation state 4 in our reactant and in oxidation state 3, so in a slightly reduced form in the nitride. So what is the reducing, what is exactly oxidizing here if titanium is reducing? I'm not sure if that has been fully figured out. And then there is still a different type to grow platinum films. This is something that was developed at the University of Helsinki a bit more than 10 years ago and has been become very popular in the world. Noble metal films by oxidizing, simply burning off the ligands. Because the noble metals, they want to be metallic, they still make the metal films even if you oxidize them. And whether that's purely burning and giving CO2 and water or some other, that might depend on the reaction conditions a little bit. And so it was in 1974 that Suntola made the first experiments, and last year, I'm not sure if you all have noticed, but Suntola received the Millennium Technology Prize for his pioneering contributions on ALD. So since then, ALD has become a major technology in the world. Not very well known. It's a hidden technology. Who would know that it's ALD inside? It's not just Intel inside. People don't know, but it's there. It's driving our microprocessors. So ALD is a variant of chemical vapor deposition. Here is, I tried to find a scheme that depicts the basic processes in chemical vapor deposition. This is one that I found. It's by Henrik Pedersen and Simon Elliott. Both are also active in the field of ALD. And I don't have the pointer here. So you have typically a continuous gas flow. These are actually the same steps as for catalytic reactions. They are not so very different, the same processes. So I'm going to put on the next one. So in CVD you have a continuous flows. In ALD you have to pulse in the reactant or precursor. I use these two words interchangeably. Reactant vapors one at a time, so that's a difference. In CVD you can have gas phase reactions happening. In ALD we want to avoid this one. So that's in ALD the good reactants, they would react aggressively with each other if they would meet in the gas phase. That's how you get them reacting well on the surface, and we want to avoid the gas phase reactions. What has not been written down here is the adsorption step, but it's obvious from the picture. Adsorption, then you can have surface diffusion and of course surface reactions, and nucleation and island growth can also happen in ALD. Then there is a step, desorption of film precursor. Well, if we have in ALD irreversible reactions, we wouldn't have this either. And then desorption of volatile surface reaction products. So it's the same scheme, but a little bit more simplified for ALD. And what we would expect and want if we think of the distribution of our catalytically active species inside a catalyst particle, we would want to get a homogeneous distribution, the same kind throughout, no matter what is the particle size, for example. But for CVD, with a continuous flow, what you would expect is that you get an eggshell type of distribution of species, so that at the outer surface of the particles you have more material than in the inside. Maybe in the inside you don't even get anything. And ALD doesn't really care of the shape of the particle, shape that you coat, so you can have planar wafers as the examples here. The catalysts, those are zirconia particles, 3 millimeters or so at least in diameter. There have been examples in the literature where people use biological substrates, like here tobacco mosaic virus coated with ALD, or you can have macroscopic objects. This is like a T-tube, or how do you call that? And then you can have also these specifically made 3D substrates I have here, and actually an example of what that SEM image is about. It's a cross-section of what we have here. So there's a narrow gap that has been made to have certain dimensions so that you can analyze how the film grows inside. So in principle, any shape can be coated, as long as the surface is reactive. So if there are no sites on the surface that would react, then you don't have any growth. Here are the typical types of reactions. Ligand exchange was also mentioned in the lecture about homogeneous catalysis. And I have to say I didn't compare yet whether that definition of ligand exchange is equal to this scheme of ligand exchange that is typically used for ALD. But in the field of ALD, typically you would think that you have an OH group on the surface where then the molecule comes in and removes that hydrogen and makes a bond to the oxygen and has some, you have the metal with some ligands, and then one ligand was removed. It combined with hydrogen and it goes off as gas. In the case of trimethyl aluminium, that would be methane. In dissociation, all parts of the molecule would stay on the surface. So trimethyl aluminium, it would also open up the oxygen bridges on silicon, making again the aluminium with its ligands, and then you have here silicon, and that would be bonded to methyl group. This is something that you can observe, for example, with silicon NMR or carbon NMR or hydrogen NMR. And then there is one further example of association. I'm not sure how often that actually takes place, but a reaction where a new bond is formed between the metal and a surface group without any ligands leaving. In principle, possible as well. Okay, about the monolayer. So in the first experiments of Suntola, he got 1/3 of a monolayer. He expected 1, he got 1/3. But that is then thinking of the monolayer in terms of the material that he wanted to grow. He wanted to grow zinc sulfide. And you know, you can calculate how thick is a monolayer of zinc sulfide, and he got on average 1/3. But we are doing chemisorptions in ALD. And if you look at the UPAC definition, once you have saturated the surface, once no longer reaction takes place, you actually have a monolayer. By definition, you have a monolayer. So these are things that, if you don't pay attention, you might get them mixed very well, very easily. But I hope that that picture clarifies it a little bit. So typically we have a metal atom or ion that is carried to the surface with ligands that are actually bigger than the metal itself. And at least in some cases, it's the steric hindrance by these ligands that causes the reaction to stop. The surface is full. And then you remove those ligands and you transform the material to an oxide or nitride or sulfide or something. And then you have those units kind of on the surface from which you then keep on building. So a chemisorb monolayer transforms to a fraction of the monolayer of the material that you make. Does this make any sense to you? Yes. And so typically, if you look at the values reported in the literature for ALD, in exceptional cases you can find a monolayer per cycle. You can find examples like that, but they are very exceptional. More typically you have something like 5 to 50% of a monolayer per cycle. And yeah, many ways to estimate the monolayer thickness. This is an extra note for those who actually work with ALD. So if you look in the literature, it's not only the history understanding that is developing, but also the nomenclature, the terminology that is being used. So you can find people using the term growth per cycle and growth rate for exactly the same thing. So the amount of material deposited per cycle. Just a quick comment on that, and those who want to read more can read more. So if you do not have any reactive sites, then you shouldn't have any growth. If you have a few sites here and there, then you are going to deposit islands. Here is an example where on hydrogen-terminated silicon, that's not typically a very good starting surface, zirconium oxide was grown. That was on the early days of developing the materials that are now in the transistors. Hafnium oxide is being used there, but zirconium oxide was also investigated, and this was a nice example of what ALD can do. So how many cycles was this? 60 cycles of zirconium oxide, and you, in transmission electron microscopy taken from cross-section, you see clearly that there are islands. And then after the sample has been taken to air, then silicon dioxide has grown underneath. This was not the purpose. They wanted to get very uniform films, and in the end, that has been managed. But in early days, people wanted to minimize the amount of silicon dioxide and ended up growing in islands. But you can also turn this around. So if you only have a few reactive sites, you only grow in those places, area-selective ALD is the counterpart of this one, and that's something that is really growing now a lot. And I do think that in ALD there are lots and lots of opportunities in this that haven't been yet fully exploited. So there's going to be the 4th, now yearly, I think, area-selective deposition workshop that is concentrating mostly on ALD and using exactly this phenomenon of island growth in a controlled way on pre-patterned wafers to grow film only where you want it to. And this is at IMEC, the place where I was also as postdoc, participating in that transistor development a long time ago. This is an overview from quite some years ago of the materials that have been developed by ALD. Over 700 processes, different processes, had been reported by that time as ALD. So it's a review, a summary of literature at the end of 2010. And if you study this in detail, you find that oxides have been grown the most, nitride sulfides, and many others. And if there is a black background for the element, then that element itself has been grown. Not necessarily at all in a process that would be industrially relevant, but at least somebody has tried it, somebody has reported on it in the scientific literature. this is large worldwide research at the moment, and you quickly see that a lot of materials are there in the place where we would expect to find the catalytically relevant materials. So these have not been, many of these have not been developed for catalysis purposes, but rather for microelectronics. That's where the big money is. But we can use these also for catalysis. And okay, this overview is old, and this is how I presented it last year. I would want to update this table, and I have done a lot already in open science collaborations, and I think that this could be updated also in a global collaboration. These are tables that have been, or review articles that are being cited a lot because of these overviews. And I would also like to develop some online system where people can add information of new processes themselves. But what happened in, I think, January this year is that somebody already did something for this. So there's a blog called Atomic Limits. It's from Eindhoven University of Technology, Professor Erwin Kessels and collaborators. So they were tired of the black and white version, and they had made it a colorful version, and then also added materials that have been made since that previous review. I find this really, really nice development. This still did not fully make void the need for this international collaboration, because here we have the same visual outlook, but actually what has been really useful in the previous version is that, so this has been published, it's available, and there are huge tables where you can find these references, where to go for to find information on those processes. So this one doesn't have the table. You have to search the literature yourself, which is of course okay also, but I still would like to sometime in the future perhaps do something for the update. But I'm really happy that somebody else has also picked this up, and this is anyway, it's better to have it updated like this than not at all. So the urgent need is over. ALD process development is active worldwide. There are many groups that are doing ALD development, and ALD is there are many people in Twitter nowadays. We have a nice community there with the hashtag ALDEP. And this is a person from the University of Helsinki. They have developed a lot of processes as the first ones. And the comment, I don't know what had happened that day, but this comment, he's now a postdoc. The holy trinity of ALD, precursor, reactant, reactor. Pray every weekday from 9 to 5. This is how they develop processes. I guess that I can interpret from here that they have experienced the same as I have many times, that the nature often surprises. And that's why this whole thing keeps on being interested. I have now 20 years of ALD career, and I think that if we would always know in advance what happens, I would have changed the field already. And okay, so more than 700 processes have been reported, but now that we want to use them for catalysis, I myself have actually little trust in that a certain process would directly be applicable for porous materials. So they have been typically tested on planar surfaces, and how well have people actually verified the saturation? The cycle times on these flat surfaces are on the order of seconds. If we want to have coatings on porous materials, it might be in half an hour that we do one reaction. And if there is a slight portion, let's say, of decomposition in this reaction, that the reactant would not react fully in a saturating way, but there would be a continuous component. You might not see it on these samples, but you would see them in our porous materials. So it's very good that there are so many processes where we can start from, but I wouldn't make any promises that they work before I have tested it myself. And then some words on the history of ALD. So it already became clear, ALD has been invented twice. Here is a comparison that I made for an invited tutorial, 2014. In the 60s, in USSR, Russia, 300, 400 kilometers away from here. And then in Finland for industry, in Russia in academic field by chemists. The area, the targets and the application areas were really different, and it took a long time before these people were aware of each other's work. And it is still so that there isn't actually any good review article which would treat these both in a balanced way, in a full way. That doesn't exist yet. I hope that we will write one from the history project. That's the goal. It's a very challenging goal, but it's the goal. In Finland, in '74, for electroluminescent displays, here is still zinc sulfide that is making the light, yellow light. So these displays have been made in 3-color displays, but never full-color displays. And catalysis applications were started already in the 80s in microchemistry. This is also something that the review articles don't really know about, or don't describe very well. And this is still less well described in the Soviet Union already in the 1960s, and first catalyst applications from '72. And now that we talk about catalysis, this is also not known in the world. In Bulgaria, there has also been a thesis. This is a habilitation degree thesis, not the same as a doctoral thesis here, but like a follow-up thesis on ALD for catalyst preparation. And you got to explain the term self-correcting mechanism of science. So this is where I would say that mechanism is active. So the fields of science, they, from an outsider's perspective, they developed by themselves. If mistakes are made, if omissions are made, these get corrected with time. But that actually doesn't happen by itself. You need active people, active scientists to make that happen. So I'm here playing a role in that self-correcting mechanism of science. Good. Now we can go. Oh yes, still a picture of this Millennium Prize. I was very, very happy. This was a dream come true for me, actually, that Suntola received this recognition. So this was last year given to Suntola. 2 years before it was the Millennium Technology Prize was awarded to Francis Arnold. And do you know what he got last year? The Nobel Prize in Chemistry. ALD for catalyst preparation. I still have a little bit here before we take a break. Okay, 4 main routes to prepare the primary solid, and ALD obviously is part of the first one. It's a deposition method, and gas phase depositions, they are listed there, and ALD is of course part of that. Uniform metal distribution should be obtainable by ALD. So these are the different distribution types from the Munich review. Homogeneous distribution, that's where we are going for. And there are examples where that has succeeded. This is from my own doctoral thesis work long time ago. With CHEM-EDS line scan, looking through a particle that is more than 100 micrometer in length, and aluminium nitride have been grown inside, and the ratio of the aluminium and silicon signals, they are the same throughout. So this is where we would be heading for with our catalyst. This is the goal of my research also here at Aalto University in this field, which is initiating now. We are not yet here. When I was doing my thesis, I was part of the microchemistry team where many people had been working with this for many years, and there was a lot of practical experience. Now we are starting a little bit from behind, but we'll get there. Specialized equipment is needed, typically vacuum equipment, low vacuum, like 1,000th of the atmospheric pressure, not the high vacuum types that you would have for TEM and XPS equipment and so on. No, much higher pressure range. Typically working at temperatures somewhere between 100 and 500 degrees centigrade. It's not only the reactions that you need to take care of and the lines that feed the reactants there, but you are working with toxic gases and they need to be carefully taken care of after the excess comes from the reactor. We have these classic reactors here at Aalto University. And in Finland, typically when catalysis research has been made, it has been made with these classical reactors in a fixed bed mode. So you have a holder for catalysts and a gas flow that goes through and away from the bottom. You can design many different types of reactors. A fluidized bed reactor would be an obvious one, which would allow you to make the reactions much quicker. But then it's technically much more demanding also. And if you look through the literature, there are many different options, rotary beds, even the FCC, fluid catalytic cracking type of riser reactor. And then many people actually, I think most of the literature now that you would read, actually people have been using the same kinds of reactors where you would put a flat wafer, but they have put there a tray with the catalyst particles, and then you have just flow over the tray. But you will understand that there will be diffusion limitations. And I would never be sure that these catalysts are uniform throughout. So the type of CHEM-EDS line scan that I showed from my work a long time ago, they are actually not typically presented in the literature at the moment. So I'm myself a tiny little bit skeptical for the uniformity, if not reported. And yeah, the F120 reactors, they have been developed by Suntola and co-workers already in the end of 80s, and we have those at Aalto University, and this is from last week from the University of Helsinki. It was a crazy week. The F120 controller gives fatal errors, and yeah, we are really relying on these reactors in Finland a lot. And I think that it would be nice to get some newer reactors, maybe make them ourselves or buy. Let's see where we are a year from now when I give this lecture again. Typically, it's expected that ALD catalysts will give a high dispersion. So I have here the dispersion example. So all the atoms that are on the outer surface, they are accessible to do the catalysis. So the dispersion, it's the number of metal atoms exposed, ratio of that to the total number of metal atoms. What's the dispersion of this Rubik's cube again? Let's do the exercise. Now I have made it a little bit easier. There you see the atoms, so to say. So we have 27 atoms altogether, and the one here at the bottom is not exposed and the one in the center is not exposed. What's the dispersion? Who would say?
25 over 27.
Yes, exactly. So I think that's 92%. I calculated before. Yeah, so ALD should result initially in single atoms that are separated on the surface, and then when you are adding the cycles, of course, the atoms get covered, and the dispersion will not be 1 anymore, but in the beginning it should be. And that should be an advantage of ALD, that you have very high, very controlled way of drawing, and here is now an example where you would have exactly the same number of atoms in a particle. Maybe life is not exactly that simple, but we can anyway present the scheme. But compared to other methods of catalyst preparation, ALD has been shown to give a narrower particle size distribution. And monodisperse catalysts at best. Monodisperse meaning that you only have like this one size at the surface. This is data from not an accessible source, but I still like to show it. It's from a keynote lecture by the now Professor Emerita Krause at Europa-CAT conference more than 10 years ago. So ALD catalyst development has been big at Aalto, or the what was before Aalto, the Helsinki University of Technology. And it is examples of how much metal you get in one reaction only of two different molecules, chromium acetyl acetonate or iridium acetyl acetonate. And this is, I hope I am able to draw this now correctly, acetyl acetonate. I think that it's a ligand like this, and here you have the metal. Those are carbons. So not a small one, but anyway the same in all cases. And depending on the support and the metal, you get 0.4 to 5.6 weight percents. Big differences. But then when you start to look at the amounts in the units that I really like to look them in, you convert them from the weight-based units, which are important because we pay by weight, always, we need to know this, but to think of the atoms on the surface. I want to see and think of the atoms. So then suddenly, if you have the alumina support and these two different molecules, you get 0.6, 0.7 atoms per square nanometer. Actually, you have the same amount. And if you then change the support, so chromium on zirconia, well, it's still not very different, 1 per square nanometer or 0.6 per square nanometer. And typically, I'm not sure if I have discussed this or if you recognize, if you think of a monolayer of a material, if you think of how many metal atoms you have there, we have seen these in the Physisorption calculations. How many of palladium, platinum, nickel, what did you calculate? How many do you have per unit surface area on a surface? These numbers, they are always quite close to 10. Not exactly 10, but they are not 1 and they are not 100. They are 10, 12, 13, something like that. So that's the order of magnitude that we are talking about. And then you can compare that to the amount. And if we talk of a monolayer, well, we are much below a monolayer here, right? 1/10 of a monolayer or something. And also what's interesting is that people think, of course, of the reaction mechanisms. Typically, hydroxyl groups, OH groups, are reactive sites. And also you will enter, if you read through the literature, people assuming that there's a 1-to-1 correlation between the number of reactive sites and the amount of metals that you put in there. But this alumina, for example, has 6 OH groups per square nanometer, heat treated in the way that it has been before the ALD. And then you put there 0.6 metal atoms. It means that only 1/10 of those OH groups actually reacts in these cases. I still have a lot here. Shall we take a break now? I think that's best. So 5 minutes break.